Thank you. Wait till Shankar comes back. Oh, so no exams for you? You don't have. You're not a student too. Who are you working with? Oh, okay. So today's, I think, at least in the morning, it's going to be a short lecture because everyone knows finite element analysis is because you had modeling in the title of the GIAN course. I thought let's do one. But I think the afternoon will have application to a specific project, funded project that'll be a little more interesting. Okay. So should we start? Okay, coming to the last day, the lectures. So this is just today we'll talk about computational models. In the morning, I'll just go over the general method, finite element method. I think all of you are familiar, but we did make one improvement on the modeling aspect, which we'll talk about. So this is the outline. We'll talk about motivation. Why do we need models in NDE? We have seen all through these last 4 days how we use models. So I'll go over the benefits of a model, and then what are the governing equation, how do we get finite element model, validation is important, and some forward problem examples. Okay, going back to the generic NDE system. So Neeraj, this recording, right? Yeah. Okay. Anyway, so this is our generic NDE system, and this side is what we call the forward problem. In the forward problem, we know what is the excitation source. So, and we know what is the sample geometry, we know the defect geometry also, and all we are predicting is what is the signal you will get for this particular situation. So this is called the forward problem. This part is the inverse problem. So given this, you don't know what is the sample geometry, and you know excitation source, of course, but from the measurement, I want to know what is the defect profile. And as I mentioned in the earlier pictures, once you know the defect profile, you can calculate the remaining useful life or what is the strength in the sample or the structure. So we also saw that in the inverse problem, sometimes you want the full defect profile, or sometimes you just want the class, a classification. For example, in the pipeline, you initially want, is it a valve, is it a sleeve, is it transition, or is it corrosion? And once, only when you classify and get the corrosion part of the data, you do the profiling of that. So this is sort of describes all the modules in a generic system. You know the exact profile, shape of the defect, and the location of the defect. Everything is known.
Where will it be practically used? Because I know everything and I'm just collecting the samples.
Okay, I'll talk about the benefits. So you are just predicting the signal. What signal will you observe if you have this kind of a situation? Okay. So why do we need modeling? So modeling just gives you the solution to the forward problem. And some of the uses are, it can be used as a test bed for generating defect signatures. Typically, when you want to train a neural network, you want to have a lot of signal data. And you cannot machine all these defects in different orientation and all kind of thing. So the model can be used. With the model, you can do anything and get the defect signature. More importantly, when you are designing the sensor itself, the coil, you want to visualize the field-flaw interaction. How does the field, you saw in that other model, field distribution, and what happens, how does it interact with the sample and the defect and the signal. So that's the other thing. So it is in this way used for optimizing the sensor and system design. And in the afternoon, I'll show you an example of simple coil design. What is there in a coil design, but how the model allowed us to design an optimum coil. And then you can also use it for probability of detection models, because in the POD model, what you really need is a variety of parametric studies. What happens to the signal when this changes? Things like liftoff is bound to change. There's a lot of uncertainty, and you also even when you model, you assume a certain value for conductivity, permeability. But that changes because of cold working and because of many other processes. These conductivity and permeability can change. So how does the signal change when that happens? Those kind of things. So POD is very, very crucial in any NDE application, because you assume that a signal is going to look like this because you saw that in the calibration sample. But in the field, things are very different. In a particularly nuclear power plant, we are looking at heat exchange tubes. We can look at some signal, but very often, because of corrosive products, a lot of debris floating around, some magnetic rust particle can stick on the outside. That's going to change your signal. So we can actually do the analysis by using the model to do all. So the computational model is extremely important. And that's why when we start any project, we first develop this model for that. Okay. And then for inverse problem, we saw that there are iterative approaches for solving. If you want to reconstruct the defect profile, you can use the forward problem iteratively. That's the other thing. So in any model, the input that you provide is the excitation source, the specimen or the test specimen, the defect geometries are fully known, material properties have to be fully specified, whether it's permeability, conductivity, permittivity, and so on. And other test conditions, if there is lift-off variation, if there is an angular tilt when you're, all that, we studied we've developed this another student thesis which was on the probability of detection model. So you have a coil, liftoff can vary, but sometimes it can also tilt. And when it tilts, what happens to the signal? So variety of things, but it's nice to quantify all this using a probability of detection and say this is how the signal is going to change. So this, we use it extensively. Okay. And the output of the model is always the signal for these input conditions. When you give all these input conditions, given a certain liftoffs, certain tilt angle, material properties, defect geometry, everything is provided, and you predict the signals. The signals could be a flux density in the case of a Hall in the magnetic flux leakage, or coil impedance, reflection transmission coefficients for microwaves, and things like that. So that's the motivation for developing a model. Okay. The thing is, you have COMSOL, for example, which does, but in order to use COMSOL, you really have to be a PhD to understand how COMSOL is working and what's the, how to give all these inputs. Even that is not so not so simple. Okay, so that's the motivation. And this is like a generic description of a boundary value problem, right? You have a solution domain, the source domain, then we have this interface, then you have this outer boundary. There are some parts as non-conducting, some parts conducting. This is for an eddy current problem. And the governing equation can be written in operator form, where you have LU equals to F. F is the source, U is the unknown. And then there are boundary conditions where U is defined on some outside boundary and some Neumann, that's the Dirichlet boundary condition. We can also apply the Neumann boundary condition on some interface kind of thing. So these are the different, this is how a generic description of modeling. Okay, so in the case of electromagnetic modeling, we start with Maxwell's equations. Maxwell's equations are usually in terms of electric magnetic fields or currents, voltages, and also potentials. So you can have this equation in terms of potentials, and eventually you have some a partial differential equation. So in EM problems, for any particular problem, the Maxwell's equations are already defined based on a particular frequency. For very low frequency or static, we have the static equation, or if you have diffusion equation for, so you have elliptic, hyperbolic, and parabolic and hyperbolic. Then you need to know the constitutive relation, and then the interface conditions, boundary conditions, and how the potentials are related to the unknowns, and so on. So this is how you set up, initial setup, till you get your differential equation, because once you have this, you can use any method for solving a differential equation. Boundary conditions are typically, the outer boundary where you can apply some kind of, if it's static, I can apply Dirichlet homogeneous, so everything is zero. That's the outer boundary. Interface is in between. You have two different material. So if you have layered structures, for example, in between there's an interface. So if I have a conducting and a non-conducting thing, then I know what happened. My current, I can't have a normal component of current density vector. So those would be the interface conditions. Okay.
And in case of the boundary condition, it's going to be either purely reflecting or purely absorbing.
Yeah. So typically the boundary condition, you have absorbing boundary condition. If you have waves, you want everything to, you don't want reflection from there. But for static and quasi-static, we normally apply just a zero field condition. Yeah.
Not sure that. A forward problem. That means you during the different type, I collect a sample of signal large enough, and that sample being used with our neural network and for using the inverse problem that if I have this type of signal, what would be the possible defect
Yes.
profile?
So that's how neural network is used in the inverse problem. At the input, you give the signals, a different signal, and in the output, you have the corresponding defect profile, and you let the neural network learn that mapping function. And then you have a test signal, it will tell you what the defect profile is. It's like a black box, I don't feel very comfortable with that approach because it's a black box and there is no physics. Well, you can say there is physics because the mapping is based on the signal to defect, mapping. So, but it's not like an analytical solution where you know exactly the physics is embedded very accurately. Here, the physics is embedded only for that range of training data that you provide. So what happens if I give a training data that was not a test data, not in the training data, not even interpolated, it's somewhere outside? That's the thing, it's unpredictable what the neural network will provide. So that's why way back in the beginning, there was, neural networks where everyone jumped on the bandwagon. They all wanted to do neural network. Then afterwards, neural network got, people sort of over-promised and it didn't deliver. So it's sort of, people started looking down on neural networks. Now it's coming back using things called deep learning and all that. But what has happened now is the large amount of data that is available. Okay, in the 90s, when neural networks, I think we were the first ones to use neural networks in NDE community. In the 90s, there was limited. It was amazing because time-wise, it is instantaneous, real time. It will give you a full defect profile. But then there are limitations. Okay, so as long as we let know what the limitations are, we can use it. But in the last 2 decades, the data, you have this big data problem. We have too much data. So we can actually, there are deep learning, new type of learning algorithms and neural network architecture that allows the network to learn on its own. So that's what's happening in AI and machine learning. It's again taken off because of the availability of a large amount of data now. There's whether it's medical data for that application, data is now much more prevalent. So it's coming back again. Okay. So how did we get onto the neural network thing? So anyway, that's the how a training data is used for the inverse problem.
Components of sine and cos.
Yeah.
Out of curiosity, that if we have any signal which is coming from a forward problem, we collect that signal. That signal can be interpreted in that way that the defect can be in form of different components of square, rectangle, or circular geometry.
Yeah. Yeah. In fact,
corollary to that Fourier transform.
Right. In fact, one of our pieces, I think I had some slides. We use what's called the radial basis function network. And in the radial basis function, there is, you can choose your basis function. So we choose wavelet basis, and the wavelets are nothing but it breaks down each layer. It breaks it down into a crude approximation and then a finer approximation, very much like a Fourier transform. So wavelet transform is like Fourier transform, but much more applicable when you want to reconstruct a defect, which is odd, So we actually have done that. You can break down, decompose a defect profile into, say, a square profile of this depth, and then smaller thing, keep adding on in multiple layers using a particular type of basis function called the wavelet basis function, which has different scales too. So that's it. Yeah, there's a lot, I've done 30 years, so there's a lot of things that we have done, but we are just presenting a little bit. Yeah. Now I have an idea. So what your interests are. If I had this discussion, I would have brought those slides over. Okay. Okay. So let's go to Maxwell's equations, potentials, and PDEs. So this is the general Maxwell's equation for which covers all frequencies. So if it's static, this term and this term will go to 0. For low frequency, we still ignore this term because the displacement current is very, very less compared to orders of magnitude less. It's 10 to the minus 9 times the conduction current that's over here. So these equations can be modified based on the frequency of operation and will provide you, so whether it's magnetic flux leakage or eddy current or microwave, this is my starting point. And we approximate it for different frequencies and do that. Okay, so these are the equations that we need. Then the constitutive relations are given over here, where the field is in terms of the material property. So these are all well known. Okay, so these are the different parameters. Okay. Okay, I will come to that. This over here, I should not have that separation. Okay, but I'm going to talk about it in the future slides. So, it's what copy paste does when I'm trying to redo all the slides and using existing slides. So, in this, ignore that for now. Okay. So these are the interface conditions. These are the conditions satisfied by the electric field intensity, electric density, flux density, magnetic field density, magnetic flux density. So if there is no surface current or accumulation of surface charge, I would have these to be equal to 0. Otherwise, I'll have to equate it to that. Okay. Those are the interface conditions. Boundary conditions can be either Dirichlet condition, which is you specify the field itself, or you can specify the Neumann, which is the normal derivative of the field, and you do that whenever you have a symmetry boundary condition. Okay, you have a axis symmetry tube, at the center we'll have Neumann boundary condition, but because whatever is here is reflected over. And the radiation condition for microwaves, any wave phenomena. Okay. So then the governing differential equation, sometimes, people have different preferences. You can define the equation in terms of E and H itself directly and solve for E and H, which means you've got to solve for 3 components, Ex, Ey, Ez, and H. Or you can just, you have the relation between E and potential, scalar potential. You can get the differential equation in terms of the scalar potential. So the formulation of the governing differential equation, whether you want the electric field or the scalar potential or a mixed thing, or the H or the magnetic scalar potential, that's a fictitious quantity. But mathematically, you can solve for psi and then calculate other quantities. The same thing, you can either solve for B, or from B, we have this magnetic vector potential. And with J, you can have electric vector potential. This again, all these are fictitious quantities, but mathematically, they provide you a tremendous amount of convenience. Okay. So why do we use potential? These are continuous values, whereas fields, we know that they have to satisfy the interface condition. So The normal component is continuous, the tangential component is continuous, but normal component is discontinuous and all those things. So very often you will find, we have used potential formulation, but because once I have in potential, I can calculate all the fields. I can calculate B, I can calculate E, I can calculate the current, anything. So that's the other additional advantage of using potential for formulation. So I don't have a slide which shows the the governing differential equation in terms of potentials. So but we all know you have Maxwell's equations, and then you have the cross, del cross H in terms of B, and then I substitute for B del cross A. I can also, there is also a relation between E and A, which is minus dA dt is E, that comes out of Maxwell's equations. Okay. I know I've not gone through all those details because there is no end to it, okay? But you'll find that in most papers, and I can send you our paper. Okay. So the rest of those are related to the electromagnetic NDE problems. Now, the partial differential equation, as I said, the static is elliptic, diffusion equation is the parabolic and hyperbolic. And typically, when you talk about a model, there are two fundamental approach, right? You can come up with an analytical model, which have a lot of convenience, lot of plus points, because they give you a closed form function. All you have to code is that one equation, and then you change all your parameters and outcomes. Everything is in real time. But analytical function, if you have worked with it, what's happening?
On the online students, things have changed.
Oh, okay. Right. So I've already finished 10 slides.
Hello? Yeah, Nima, we just figuring out. Just give me 2 minutes.
Can I display settings? Swap. Okay, what about this thing? Will this do it?
No, that actually you can see it here.
Okay.
No, it's not from your setting.
I know, but in the process I've changed. I want to go back to what I did.
ये वाला?
No, hyperbolic is wave because you have second order derivative, time derivative. It's a wave equation. Second order spatial, and this is a first order time. It's a diffusion. You have a look at thermal diffusion or any kind of diffusion, it's only first order, damping kind of thing.
Hello, oh, I think again it changed.
Yeah. Diffusion, you're always trying to calculate the unknown U, okay? But the governing equation varies in space and time in this manner. That's all. That comes out of the Maxwell's equations. You will come up with, for eddy current, you will, if I don't look at the steady state case, I will have for a pulse eddy current, I really have a diffusion equation. That's what happens. The E field, the current density, the flux, everything, all the whole field, falls. It depends on what your unknowns are. If I do it in terms of J or B or H or E, that quantity is diffusing with time. When I apply a pulsed field, and as it propagates into the sample, it will diffuse. It will follow a diffusion equation.
नहीं, शेयर तो स्क्रीन से जो दिख रहा है वही शेयर हो रहा है. हाँ सुधीर. हाँ. नहीं हो रहा ना वो, इसीलिए मैं तुमको पूछा. हेलो. वो स्लाइड्स नहीं. हाँ, तुमने जो सेटिंग करके किया था उसमें कैसा है कि नीचे का पूरा वीडियो दिख रहा है, स्लाइड्स नहीं दिख रहा है. स्लाइड्स छोटे में जा रहा है. तो वो पर स्लाइड्स नहीं दिख रहा है ना बीच में. अभी नहीं दिख रहा. अभी स्लाइड्स भी नहीं दिख रहा है डबल क्लिक करने से. सिंगल, हाँ हाँ. ठीक है. तो ऐसा कुछ चेंज नहीं, वो तो फुल स्क्रीन और वो हो रहा है. 3 4. डबल क्लिक ही कर रहा हूँ सुधीर, डबल क्लिक समझता हूँ मुझे भी तो. हम्म हम्म. ये नीचे नीचे अलग अलग ऑप्शंस हैं बट उसमें कुछ हो नहीं रहा है, मतलब स्लाइड्स नहीं दिख रहे हैं अभी. तो कुछ नहीं आ रहा है अभी. तुमको टाइम लगेगा क्या? हाँ तुरंत भेजो उसको. हाँ.
Nobody complained in the beginning.
हाँ, एक्चुअली शी टेक्स्टेड बट
Oh,
शी मस्ट हैव सेट इट इन द चैट. या. स्लाइड्स क्यों नहीं दिख रहा है? स्टॉप शेयरिंग फर्स्ट. This is the one, na? Here it is.
so this is WebEx, not.
No, they have a different setup, and through WebEx we are sharing it to the outside world. And इसमें यहाँ से जाके स्लाइड्स क्यों नहीं दिख रहे हैं मैम के? So
Comics,
स्लाइड्स नहीं दिख रहा है.
स्लाइड्स में दिख रहे.
नहीं.
Okay. How many PhDs does it take to get a PowerPoint presentation?
हाँ सर, बोलिए सर. हाँ हाँ
N+1.
सर, टीवी का तो किया हूँ मैंने.
Let's see, what is, where N is the number of academics in the room who think they know.
नहीं नहीं, ये
and
लेआउट
what is
चेक
the
करना है
person who
आपको.
What?
See that comment. That's what's happening.
How many?
छोटा वाला तो लेआउट लिया पर
Answer is N+1.
N is the number of people working here, and N plus 1 is the one you're calling on the phone.
वो तो किया सर मैंने
Yeah.
वो तो किया मैंने सर ये
Always, yeah, that's true.
दो लोग दिख रहे हैं ना
हाँ हाँ
नहीं तो स्लाइड्स चाहिए ना स्लाइड क्यों नहीं दिख रहा है
This is also gone now.
स्लाइड दिखाना है ना स्लाइड्स नहीं दिख रहा
कहाँ
है।
से
ये जो कैमरा है
हाँ,
ये
हाँ।
छोटे में मैम को दिखाता है और एक
नहीं वो तो साइड में हो गए सर वो हाँ बट ऐसा बोल रहे हैं सर
हाँ यहाँ पे स्लाइड
स्लाइड आना चाहिए था।
एक्चुअली वो स्लाइड्स के बारे में पूछ रहे सर डबल क्लिक ही किया सर मैंने हाँ बराबर है सर अब उनको पीपीटीज दिखाना है सर
हाँ
सर पीपीटीज दिखाने के लिए बोल रहे हो
सर योर पीपीटी इज विजिबल।
That's also gone when you
अच्छा, हाँ, हाँ,
unplugged it and went.
या
It's gone too. So
इधर पे भी नहीं दिख रहा है इधर पे भी नहीं दिख रहा है।
सर एक मिनट रुकिए सर मैं
I have already stopped sharing.
something with this. This was gone to the projector at least before.
नहीं दिख रहा है नहीं दिख रहा है वही बोल रहे पीपीटीज नहीं दिख रहे
Reboot everything.
नहीं दिख रहा है
Wait, this one, what he normally uses something over here.
That's for mic.
Oh, that's
For
only for
mic.
mic. That's correct.
That's
Yeah.
audio.
सर ये हाँ ये है एक्चुअली एसडीएमआई लैपटॉप है ना
Now,
फ्रंट टीवी पे
wait, it will come.
back.
Oh, that thing is, the screen is going up.
You press this button, this is off.
Oh, okay.
Press one time, it is on.
Yeah.
And, second time off.
That's easy to fix. How do we get that? Okay, something's happening now. Can select the PPT there,
Yes, this is WebEx.
sharing.
Share.
हाँ सर ये हाँ हाँ सर एक
मैं कहाँ खड़ा हुआ था?
X panel.
ये कहाँ से होता है ये मिनिमाइज करने के लिए
पैनल है ना वो मिनिमाइज करो ये लेआउट चेंज करो यहाँ
हाँ
का
हाँ
हाँ एक्स पैनल खोलो
हाँ सर एक मिनट
हाँ इसमें पासवर्ड डालिए 1 2 3 4 5 6
हाँ हाँ
एंटर
अनेबल करना है इसको
नहीं प्रेजेंटेशन लिखा है ना पिक्चर
हाँ
HTML करो
ठीक
अभी देखो आप अभी देखो इसको मिनिमाइज कर
हाँ आगे है ना
ये उल्टा हो रहा है।
उल्टा हो रहा है।
लेआउट पे कीजिए
लेआउट में जाओ, इधर नीचे
इसको डबल क्लिक करो बीच पे डबल
आगे
आगे
ठीक
शेयरिंग करना।
पर मैम का स्लाइड कहाँ दिख रहा
It's open.
है?
No, well, not minimized.
हाँ हाँ किया है हो
Okay.
गया
Now okay.
It was not minimized. When I just went into it, was on slide show. Now it's working.
बोलना
नंबर
good.
एक बार वेबएक्स में देख
हाँ सर, हो गया, ये आया है।
So can you check with those online students if they can?
Yeah.
शेयर में कुछ शेयर करूँ? क्या करना है? कंटेंट? मीटिंग विंडो की क्या शेयर
कर दो ना
है ना?
ये है ना
हाँ, आगे
आगे यस ऑडियो
So, okay. Okay, so far we have looked at all that's needed for formulating the governing equations for the electromagnetic and E problem. The next thing that was over here, depending on the operating conditions, you can have either an elliptic equation, a parabolic or hyperbolic equation. All this can be derived from the Maxwell's equations, either in terms of the field quantities or in terms of the potentials. Okay, and there's a lot of advantages, conveniences when you use the potential. So, category of once you have the differential equation, you can either solve the equation. The solution of that equation is your model, right? So you can have an analytical model which gives you a closed form function, and it's very good for simple geometries. You have infinite half spaces, and you have a coil. You can solve for it. It's still not so simple, but it can be done. Once you have the Green's function for the problem, you can use the integral equation, a solution, an integral solution of the underlying differential equation. But when you have nonlinearities and you have very large geometry, very complex geometries, analytical models fail. So for such problems, you need a numerical model. They can handle the geometry is not a restriction, not a limitation, but they are computer intensive. But these days, the resources are growing so fast, it's not a problem. Most places, universities have cluster computing, which are high performance, can be done very, very fast. Okay. Things that used to take days now gets done in hours or sometimes minutes. So among the numerical methods, there are several. There is finite difference and finite element. Those are the two main. And then boundary element is a hybrid. It's a volume, is an integral method formulation with some from numerical computation of the integrals. So it's a hybrid. And meshless is another variation of the finite element where you don't, there are some advantages. In fact, Yiming's wife's thesis was on meshless model for eddy current problem, and so on. Okay, so those are different methods. So we are going to focus mainly on the finite element methods because these are very well established. It's very stable by looking at the formulation, it provides the, ultimately when you have a numerical solution, you're taking a continuum and converting that into a matrix equation. You've got discrete points where you want to solve for the unknown. So you have a matrix equation. And the nice thing about finite element is it's a banded matrix. It's very stable. The condition number is very good. So it solves, you can solve that very easily. For most reasonable size, when you have, of course, million by million matrix, then you go into iterative problems, and there also you're looking for convergence. And when you have a good condition number, the convergence is faster. Whereas if you go into even integral equation, volume integral equation formulation, you have a matrix, much smaller matrix, but it's a full matrix. And that takes just as, so it's more difficult to solve those kind of matrix problems. So we have always looked at finite element as our staple for all modeling problems. So the first step in finite element is the discretization, or you have discrete domain in which you minimize some kind of a functional. It's also referred to as generating the finite element mesh. If you have a three-dimensional, domain, these are some of the prism type, the tetrahedron or hexahedron, trapezoidal. Those are the elements into which you discretize your whole domain. In 2 dimensions, of course, you can use triangle or rectangular elements. Okay. Then some of the things that you need to keep in mind when you are discretizing is you've got to make sure that you avoid high aspect ratio. To the extent you can, the elements should be, the dimensions should all be comparable. So the aspect ratio is as close to 1 as possible. Because everything, if all this is not done properly, then it ends in a convergence problem, and because you're trying to invert a matrix, and that's the problem there. So you have to avoid big jumps in element size. Typically, wherever there is a large gradient, you know that near the defect that the field is going to change very fast. So whenever there is a fast by Nyquist sampling applying the same criterion, you've got to use smaller elements there. You've got to sample closer when the field is changing very fast. If the field is going to be very slow, then I can sample larger spaces, so my elements can be larger. And you want to minimize the number of elements used so that your matrix equation is smaller, and those are the kind of thing. So in eddy current, whenever you have a skin depth phenomena, the guide rule is that you should have at least 5 elements within 1 skin depth. Okay, use a dense mesh to catch gradient. This is what I talked about. With a large change, a rapid change, use finer, smaller elements. Fine mesh density has to be large. But in general, if you're just making finer and finer mesh, it doesn't mean that your result is going to improve. Sometimes, if you just make finer mesh, it's going to result in a larger matrix, and it just leads to computational error. Because typically, so what we really do is we start with the smallest mesh and look at the accuracy of your result. Accuracy doesn't change, we stop. So we want to use the smallest mesh, but these are some preliminary care that you need to do. You need to take care of these things before you start your modeling process. Okay, so this is the finite element method itself. I think from the differential equation, you basically get an integral functional, which is the weighted residual, which you want to minimize, right? And then you choose basis functions within each element, and these basis functions are typically this is a linear case of a linear basis function or a shape function. So the field value at any point in the element can be written in terms of the nodal values, and this is general finite element method. And you can use a shape function in this manner. You can have either nodal shape function or an edge shape function. So there are different types of finite element methods based on that. And when you minimize R and you use the shape function approximation within each element, you'll come up with an elemental matrix equation, which you combine, assemble together, and come up with a global matrix equation for the whole domain. These are what COMSOL does or everything, so I don't think, you need to spend more time. Nobody does all these things anymore because you just use COMSOL, right? Okay.
Know that what type of defect. Depending upon the application, you can if we are going to use the frequency of EM as per the requirement of the material and all. So then
Right.
we can predict that what should be the mesh size. That means depending upon how much variable or how much variance is going to happen in that defect.
Yeah.
Select, for example, if you have a huge bridge,
Right. Right.
running for let's say a kilometer of bridge, 1 kilometer is the bridge size. And if you want to analyze it, and let's say it be a metallic or any composite bridge, and you want to analyze the wave. So in that case, at kilometer, that 1 centimeter will not be of much concern. So
Right. See, when you in the case of static and quasi-static, like eddy current, it's a very local phenomenon. Even if you have 1 meter, then I'm just going to model around the defect. That's all I'm going to model. Look at the signal. If you have wave propagation, it's a different ball game, really. If you have those are different problems, and maybe analytical way or a semi-analytical method is not what needs to be used. So that, if you have a wave, if you have ultrasonic, if you're trying to model ultrasonic wave, ultrasonic inspection or a microwave inspection, it will be a slightly different problem. Yeah. But in general, okay, when you're doing the forward problem modeling, even if it's 1 mile or 100 miles, you are only interested in the region where there is a defect. You are only interested in the defect signal, okay? So you can still always truncate it to a smaller region, apply absorbing boundary conditions so that the wave keeps going, and look at it that way. Okay. So this is in any finite element, starting from a differential equation, the end product is this matrix equation, where each element of the matrix is an integral, okay, and it depends on, for each element, it's going to depend on the nodes that are the elements that particular node is connected to, okay, because these are the unknowns. X is defined at every node in your finite element mesh. Every node is connected to multiple elements, okay, so you're going to integrate over all those how all those elements contribute to that particular node. So that's a standard thing. It's not in this particular case, a standard finite element code. So this is the key thing. Once this is set up, then the next thing is to just solve this matrix equation for B, and B can be directly the field itself, or if it's potential, then I have a post-processing to calculate the field from the potential.
Here's what I found.
It keeps doing this. Okay. This is, it can be anything right now. Okay, that's a good question. This particular one is in the spatial domain. Finite elements are in the spatial domain. So when you have a time varying equation, typically what is done is in the time domain we do finite difference, and at each step we do a finite element for the spatial field. So that is how, I did show an FDTD formulation where you can take your differential equation and discretize your time and space in the formulation and solve it. But since in the spatial domain, since finite element gives a much more accurate and efficient way, very often some of our pulsed eddy current models based on For the time domain, it's finite difference, and for the spatial domain, we use finite elements. So that, but this particular one is spatial domain is at one instant of time only. There's no time variation involved, and most of our models where we just have eddy current or flux leakage, this is enough because the continuous excitation of in eddy current, you just solve for the phasor, and once you get this E field, you can always multiply by e to the j omega t and get your time domain solution. But for single frequency, it's really there's no time variation involved. Yeah. Yeah, right. That is also true. When you have a, yeah. Yeah, that is true. That is very true. So in fact, when we do pulse eddy current, so pulse eddy current is a pulse. If you take the Fourier transform, I know exactly what the Fourier components are. Then I do the finite element at each frequency and then take the inverse Fourier transform and calculate my time domain signal. That's very, very common way of doing it. Yeah, you're right. So you guys know all about the modeling, really. I don't think I need to spend too much time. So frequency domain, all you can say that all these modeling is only frequency domains for single frequency only. But you can use, so when you use multiple frequencies though, you got to keep in mind that at higher frequencies, the skin depth is smaller. So my discretization has to be larger. So those are the kind of precautions you've got to take. But it is and you know, doing everything in frequency domain is much more easier than doing the time domain thing. You know, it's things like that. Yeah, right. Good. Okay, so once you solve the matrix equation, let's see. This is the local system. Okay, this is the same thing. We have elemental system. You know, you form the matrix equation for each element, assemble to form the global elements, global matrix equation, impose boundary conditions now. So to see which values are Dirichlet boundary conditions, those values should be used in the right-hand side. And then you solve the equation. Solving the equation is another big area of research. You know, the matrix, the linear, there are many, many libraries for a variety of methods for solving differential equations. I think we have a semester-long course on just solution to a linear systems of equation. So you can use a direct solver, the LU decomposition, or Gaussian elimination, or Gauss Seidel. There are many different ways. Or you can use iterative solver like the conjugate gradient and other kind of things. And we also, if you use iterative solver, it is good to precondition the matrix. We use some incomplete Cholesky decomposition, or there are very standard libraries of these. So there is, I don't want to get into that thing. So once you solve for these unknowns like X, if that is the magnetic vector potential, I have to now calculate what is the B. Del cross A is B, and coil impedance is an line integral or integral around the coil gives you coil impedance. So those are things that are pretty much solved. Okay, this is just the preconditioning that we talked about. It transforms the linear systems into one that has the same but better spectral properties or better condition number. As the name suggests, it's basically a different, there is an algorithm, you do it one time, but then the solution becomes easier. Now, the next slides, this is related to modeling of eddy current. Now, if I want to model the eddy current signal, I'm going to be moving my probe. Right, you saw in that other demo where I have the probe moves through. I think I'll probably show the demo again for the online students because so every position of the coil, I have to generate a mesh, do the full-fledged problem. Okay, so one way of so you've got to remesh every position. So in order to handle this problem, And there is a very efficient way to do this. We use what is called as uh, the reduced vector potential formulation, which sort of avoids the need for remeshing at each point. So we basically take the mesh. Okay, I'll probably I have the couple of slides on that. So this from here, this is another thesis where we took the basic finite element and made it a lot more efficient for scanning operation. When you have a two-dimensional raster scan, that means if I have an m by n, I have to do the remeshing, do the full matrix formulation, the preconditioning, and everything. So there is a way, so what we did was to decouple the source coil and the rest of the geometry, okay? And the coil field is calculated using Biot-Savart law, right? That is a simple integral equation. So there are benefits of not meshing. It's easy to model the geometry with complex shaped coil, particularly when we go into that plus point with a ferrite core. It's a very complex mesh, and this avoids the need for doing that. And we don't have the coil elements anymore, so the convergence rates are better. The solution domain is smaller, and so we can, you can change from one probe coil to another probe coil without changing the basic finite element model. And you can scan, you can model the scanning without remeshing the coil at each position, okay? And only one incomplete factorization would therefore be needed. So it reduces the time quite a bit. And so this is a formulation using what we call the reduced vector potential formulation, where the source and the induced fields are separated, okay? So here I can write my magnetic vector potential, or magnetic field is written in terms of the source and everything other than the source, separate out the fields. So these are the flux density and field intensity with respect to the current density Js, which is the coil current, okay? And so these are all the equations for the source. And so what we do, okay, these are the equations. This is just for getting the total equations. By eliminating all the source terms, we put all the source terms in the right-hand side. You'll see over here. So in this proposed formulation, okay, I don't think I have all these are the basic governing equation, okay, in terms of the magnetic vector potential. And now I take my A and I write that equal to AS plus AR, okay. And JS is simply this value. And of course, you have to make, this is Coulomb gauge that is there in the overall governing equation itself. So what we do next is keep all the AR term, all the source term can now go to the right-hand side because it's all known, okay, it's known values. And the AS corresponding to a particular current density, source current, can be calculated like here, using the Biot-Savart law. Okay, where is that? Okay. Okie-dokie. Okay, so once we do that, we again get a system of equations which is a lot, which has taken out all the source terms, okay? So basically you have AS, the source potential can be calculated. This is the Biot-Savart law, and this is the field due to the current. So all this is calculated one time for a particular coil geometry, and we just use the fields that are calculated using the Biot-Savart law we interpolate that to the nodes of the geometry. So this is an improvement that we came up with for all the EM problems. And of course, then we validated it. Okay. So this is the final modeling procedure. We generate mesh without the coil. Now we don't have to, when we generate the mesh, we don't have to mesh the coil. Choose basis function. Okay, these are all the same repeated thing. Okay, so generate the system equation, and preconditioning is done one time for that geometry of the sample. And then we impose the boundary condition, okay, precondition, the C matrix. and loop over the coil position. For each position, we just calculate this is just calculated once, but you have to now move those fields to the coil position corresponding to that. So generate the right-hand side based on that, and then impose boundary conditions, solve, and coil impedance is then calculated. Okay, so the advantages again is we don't need to couple the coil and the geometry. The system matrix will remain the same. It's only dependent on the geometry of the sample and defect. Okay, it's only the source field that is changing. So basically, okay, so instead of moving the coil, we're just moving the source field. So that's okay. So that is actually, the different modeling aspects. Of course, there are a lot of commercial software that will give you for the EM problems. Okay. But what I want to show in it's close to 12 right now, but what I want to do in the afternoon is we have had two major more funded projects. One is still ongoing. Okay, let me do for the benefit of the online students, let me show the video of what a model implemented in 2-dimension looks like. Okay. So this is the reduced vector potential formulation, 2-dimension, axisymmetric geometry, triangular elements. We choose geometry, which is support geometry. Support plate is there. So this is the geometry, support plate, differential coil. This is the tube wall. Then you mesh it. So you provide all the dimensions, and this is the mesh that is that's what the code generates this mesh. Here you can see the tube wall, and you can see how the element density is very, very high at the tube wall, and exponentially becomes larger and larger. You can't directly change. And this region, you have to keep it uniform discretization because the probe is moving. And this is the support structure, which has a high mu value. Everything else is non-magnetic. But you know that when there's a large mu value, then it sort of changes the flux pattern quite a bit. Okay, so going further, we now have to introduce a defect. So we zoom into the tube wall. So this is a tube wall. The defect is given the material of air. The blue is the tube wall. You can just draw a rectangular defect, or you can individually select element by element and provide an very arbitrary shape defect. And then the probe is moving, and this is in real time. You're solving for everything. Okay, this video of course was created, but this was actually a screenshot as the program was running. So when you have a 2-dimensional mesh, a MATLAB code on a simple PC, it is very, very fast. Okay, so this is okay. In the previously, oh, did we? I think I should go back to that thing. I didn't show the signals. Okay, so when you see when the coil is moving, what you're seeing the three plots on the right hand side. Oh, I can't use this. So what you see over here, this is the real or resistive part of the coil impedance. This is the reactive part of the coil impedance as it's with space. And this is the real versus the imaginary, or what we call the complex impedance. So this is, all these things are what you observe on a real eddy scope. So this was a great training tool for EPRI to train their. So you can see how the flux associated with the coil is changing too. Okay, and there are two coils, so you can see that. Okay. Okay, so what you've seen, this big lope is because this differential impedance, we just went past the edge of the support plate. The defect is still not started contributing because you can see the defect is out here, and the flux changes are because of the edge of the support plate. The difference is in the two coils. And when it moves, when it's exactly symmetric, for example, oh, I've already gone through that. Okay. When it is symmetric, it comes back, and then you have this thing is your defect signal. So it's okay. So what's the next simulation is, earlier we saw that the defect was right in the center, was symmetric about the support structure. So we have a symmetric signal. Now in this next demo, you're going to have the defect close to an edge. So that means the geometry is no longer symmetric, the signal is no longer symmetric. That's what you're going to see. So I'm going to put the defect right here, which is close to the edge. And then we start again, run. Okay. And you can see now right over here, you can get both the contributions will come together. And then we'll just have the second, this lobe is only the support plate edge. There is no interference with the defect signal. Okay, so this was the two-dimensional model. Afternoon, I'll talk about the three-dimensional model, the model validation, and all kind of. Yes, when you have axisymmetric, it means that the defect is a ring. The defect also has to be symmetric. So such a model has very limited application. You're right. It's everything is axisymmetric, including the defect. So that's why we really need a, but this was a good way to show the power of modeling to industry. It was, we just had to convince them how easy it is to apply defect geometry and predict the signal. Okay. And so this was a demo that got us, this was a presentation I made at one of the EPRI conference. And based on this, we got the modeling project. And that funding is going on now in its 12th year. It's not a defect, yeah. Right. We have done things like, support structure doesn't have defect, but what happens is there are, in this, see, right now there is no space between the tube wall and the support structure, but in practice, there is a gap. And in that gap, all kind of rust and deposits get, a lot of rust gets deposited. And that produces own signal, whether it depends on whether it is a magnet, it has a lot of rust particles, it also has copper. So the conductivity and permeability properties is very, very challenging how you model. But there is very little we can do to model exactly how the conductivity. We have to have some kind of a bulk value. So we have modeled that. We haven't. It's very. We have, for the fun of it, we can put some defects over here, and if I had. So what happened is I could have brought the code with me. But that code was developed 10 years ago, and we don't have that version of MATLAB. So we can't run that, we can't recompile and run that code anymore. So all I had was this video that we had, which we had prepared. So that's what I brought. But if I had the code, I could have gone there and interactively put a defect in the support structure and looked at the signal too. Yep, all that can be done. Yes. Yes. Yep. They are different materials, and but so the signals will show complex signal, and it's the same thing to some extent. If you put in we are not putting a metal loss type of a defect, but we are adding some other material of different property, and looking at the signal. But basically, the power of modeling is is there. And in the afternoon, I'll show two of our projects where we have used the model so effectively. And one is in the first project for EPRI, which is just the same geometry, heat exchange tubes, steam generators, because EPRI's, the different utility companies wanted this model to train for a variety of purpose, for designing coil design, for training their operators so that they can create different type of defects, different type of deposits, and see what the signal looks like. They also use it when in the field they observe some kind of a strange complex signal that they've never seen before. Then they come back to the model and iteratively they have some idea. It could be due to this or this. But those things can then be modeled, and we can look at the signal and see where you have maximum, agreement with the experimental thing. So the reason why we have this model for EPRI is for a different purpose. But the second project that I'll talk about is for the Air Force, where we designed the sensor and we use the model to do a lot of signal sensor optimization. So I'll talk about those two things in the afternoon, two different projects. About what? Oh, that's a full thesis. It's, in the meshless model, basically you just put nodes. There are no elements. There's no mesh, but there are nodes only. And you have to have some kind of basis function. So if I have, every mesh has its sphere of influence, and with it that you define some kind of a radially symmetric basis function type of thing. Okay. And so you have to sort of do everything that we did. Eventually, that also results in a matrix equation. The different, so the way you get to the matrix equation is different, somewhat different. In a way, because I don't need two small elements in the defect area, it is a little more efficient for modeling narrow cracks. For example, all I need is these nodes. Well, I wouldn't say that's not totally true. I will have to have denser particles over there, number of nodes. It's called a particle cloud. We model the whole continuum by nodes or particles. And ultimately, it's the same kind of a basis function expansion, which gives you a matrix equation. But everything that we did here, all the housekeeping has to be done without elements. I can, yeah, it's for some reason, I don't know, we didn't have anyone else to work on it. That's another area. If anybody is interested in working further, pursuing that, I have one thesis which I can send it to anybody who's interested, and you can build on it. Okay. Yeah. At each position, okay, we do it once. At one time, we'll mesh it. Okay, let me go back to that. Where is the? Okay. I need the, okay, here. So basically, where is that? This is the equation. Okay, next one. So basically, these are the equations, okay, for source field. So what I need to do is compute AS. I can use the mesh, any arbitrary coil geometry, which I'll show some of these in the afternoon, and you numerically integrate, evaluate this integral. So that means I have the field, the source field is known. I don't have to mesh it. Once I've done it, I have the field calculation. I just use the field, wherever the coil is going to be. Yeah. Because see, the thing is, in eddy current, in the problem that I'm looking at, I am suppose you just imagine I'm doing a raster scan, right? So if the coil and the geometry were all integrated, at each position of the coil, I will have to do, it's a different finite element problem. I have to mesh the coil, I have to mesh the sample, I have to input the source and then do that, okay? And now I'm decoupling it. That means now the coil geometry has changed. It's a pancake coil to a plus point coil. I have to go back and redo everything. Now I decoupled the geometry and the coil. So I have a module that will model just the coil, whatever the coil geometry, calculate the field using just this equation. Oh, I just have to numerically evaluate these integrals. Once I do that, I have my source field. The source field is interpolated onto the sample nodes. And then I just solve it, that's it. So that, yeah. So the benefit is basically I don't have to include the coil mesh at each position. That means the geometry, the source, the test geometry element, the matrix has not changed. Only the right hand side changes. So I just have to precondition it once. Otherwise, everything is repeated at every step. Yeah. Yeah. So basically, the source is only on the right hand side. So I just have to change the right hand side with the interpolated fields at each point. It's a lot of convenience, and this was 2005 PhD thesis, and since then we've been using this for all our modeling. No, I've had a lot of fun doing in academia, I'll tell you, last 3 decades of. Key is again having good students, tell you. Can give ideas, but you need students to stick with it and work on it. Okay, the 2D code that I showed, that was completely done in MATLAB. The mesh generation, the matrix formation and the solution, everything was done on MATLAB. But the 3D code I'll talk about is actually, it has many parts to it. The solver, the global solver global matrix formations, that was all done, is all done in Fortran. This was a legacy from my student days, that because everything was done, we did all Fortran code. But the solver we have taken from there. The GUI, we also developed a interface so that, you saw in that briefly, the user can select the geometry, can input what's the pipe, the tube ID, the inner diameter, outer diameter, what coil. So we have some commercial coils. It's a pull down menu, they can select a particular coil, and then there is the mesh generation, all the GUI part is done in C++. Mesh generation, I think, is done in MATLAB. So everything is integrated together. Now, once the Fortran solves for the magnetic vector potential, we have to calculate the impedance, the B value. That post-processing is also done in MATLAB. So there are several parts to it, which is all integrated into one build. So we'll look at the 3D model today in the afternoon. Yes.
Any questions from online participants?
They can unmute and talk.
Hello, am I audible? ओके, ऑडिबल तो है ना? ओके, okay, then we'll wind up this session. We'll meet again at 2:30. Yeah. Can you off for the mic?